Hello everyone. Today we'll be doing the AP Physics C problem set 13. There's only 12 questions on this one, so shouldn't take too long. We'll start with question 1. So two masses M1 and M2 have a center-to-center distance R. The masses attract each other with force F. What is the gravitational force between the masses if the R is doubled? So the equation we'll have to use for this is on the formula sheet. It's force due to gravity equals G, the gravitational constant, times M1 times M2, which is the two objects you're measuring the force due to gravity between, over r squared, r being the distance between them. So I'll denote this as force due to gravity 1, and now it's saying this equals force F. So what is the gravitational force between the masses if the r is doubled? Well, now using the same equation, which I'll denote as Fg2, it's just going to be the same exact thing, g times m1, m2, but this time over 2r squared. Well, we'll notice the only difference is this will end up becoming a 4r squared on the bottom once you square this entire quantity. So it's going to equal 1/4. I'm just going to take out that 4 so it'll be easier to see. Times g m1 m2 over r squared. And we know this value is F. So the gravitational force with this of Fg2 is going to equal F over 4. And this is our final answer, as this question is asked for in terms of F. It's a multiple choice question, and so yeah, that's what it's asking for. All right, and then we'll move on to question 2. A 0.5 kilogram object weighs 20 newtons on the surface of an unknown planet. Determine the mass of the planet if its radius is, that's supposed to be 10 to the 6th, sorry, 4 times 10 to the 6th meters. So once again, we'll write the same equation. Fg equals equals g times m1 m2 over r squared. And now with the values it gives us, we have this is going to equal 20 newtons, as that was the object is given to us. So 20 equals the gravitational constant g is 6.677 times 10 to the negative 11th times m1, which is 0.5 kilograms, that's given to us, times m2, I'll denote as just big M, which we don't know, we're trying to find, over 4 times 10 to the 6th, and this quantity is squared. And when you solve this equation for M, you end up with M equals, once you do it on the calculator, it's 9.595 times 10 to the 24th. And don't forget your units, kilograms. That's our final answer. Alright, so then question 3. The mass of the moon is 1 over 81 times the Earth's mass. Determine the distance from the Earth's center to the point where the net gravitational force between the Earth and the moon is 0. So the important thing to understand from what this question is asking is it's saying if you have a third object and you were to put it in between the Earth and the moon, how far would the object be from the Earth to where the net force coming from the moon and the Earth is 0? So in order to do that, we're going to know Fg of from the Earth is going to equal Fg from the moon. So we'll start off, Fg from the Earth is going to equal, G times M1. This is our third mass. It's arbitrary. We don't need to know it. We don't know it. We can set it equal to anything. It's just a third object times the mass of the Earth over r from the Earth squared. And now this is going to equal the force from the moon, which is going to be G M1 once again, the same object, but sometimes the mass of the moon. And we're given the mass of the moon is 1 over 81 times the Earth's mass. So it's going to be ME, and I'm just going to set this all over 81 r squared. And this is r from the moon squared. So now we want to solve for RE. So we can cancel out these G's, we can cancel out these M1s, and we can cancel out the MEs, and we'll get, not equal, sorry. We'll just get 1 over RE squared equals 1 over 81 rm squared, which is going to turn out to be re is going to equal 9 times times rm. So we'll know the distance from the Earth. It's going to be 9 times the distance from the Moon. That's our final answer. Made this annoying for myself. Annoying. There we go. Oh. There we go. All right, number 4. The radius of an unknown planet is 3 times that of Earth. If the planet has the same density as Earth, what is the gravitational acceleration on its surface? So, the first thing we have to understand is the density is equal to the mass over the volume. And we also know that the volume of a sphere is 4/3 pi r cubed. Okay, so we're trying to find the gravitational acceleration on its surface. So gravitational acceleration, or I'll start by writing this equation. Fg is equal to g times m1 m2 over r squared. And this is the force due to gravity, which we also know is mg. Now, m is referring to the mass of the object. So I'll say m1 is the object, and we'll say m2 is the mass of Earth. So I'll change that to me, so we don't get confused. And we're trying to find this gravitational acceleration here of the bigger planet. But this is just to understand how we'll be able to find that. So we can actually cancel out these m's, and this will no longer be an equal equation, but don't worry about that. So that means that g, the gravitational acceleration of Earth in this case because of me, but of any planet is going to equal the gravitational constant times the mass of the planet. So I'll just change that to mp over r squared, and r is the distance from the center of the Earth, or the center of the planet, to its surface. So this question is going to be asked we can actually solve for it because we know that the gravitational acceleration of Earth is 9.8. So we'll set that as well, and we're going to find a numerical answer for this one. So using this equation that we have found, we know that GE equals 9.8, right? Which equals G times the mass of Earth over r squared. So if we're trying to find the g of the planet, well, it's going to be g, the gravitational constant, times the mass of the planet. Well, we don't know the mass of the planet, but what we do know is its radius, and we know that it has the same density as Earth. So what we can do is we can solve for the volume of the Earth over here. So volume of the Earth is going to equal 4/3 pi times r of the Earth squared. So that means we know the volume of the planet, because we know it's 3 times the radius of the Earth, is going to be 4/3 pi times 3r of the Earth cubed, right? Which means once you cube all of this quantity, it's going to be 27 times the volume of the Earth, because the cube will distribute to the 3. So the volume of the planet equals 27 times the volume of the Earth. But we know that their density is the same. So that means that the mass of the planet must also be 27 times as big in order to get the same density. So that means it's going to be G times 27 times the mass of the Earth over, and now it's going to be 3r squared, because we know it's got 3 times the radius. So now when we solve this, we'll actually get 27. I'm going to take that out for now. So it's going to be g times me over, and now this, when you square this, it's going to become 9r squared, right? I'm going to take the 9 out as well. So remember, there's a 27 on the top and a 9 on the bottom. So it's going to be gme over r squared times 27 over 9, which is just going to simplify to 3. So it's going to be 3 times gme over r squared, and that's our value here. So g of the planet is going to equal 3 times g of Earth, and we know that the g of Earth is 9.8 meters per second. So we get our answer of 29.4 meters per second, so gravitational acceleration. So this question is mainly about an understanding of density and how to manipulate the force due to gravity equation to find the acceleration due to gravity. All right. Okay, question 5. The radius of Mars' orbit about the Sun is 1.5 times that of Earth's orbit. Determine Mars' orbital period. Okay, so the most simple way to do this equation is having an understanding of Kepler's law of gravitational acceleration. It's Kepler's second law, I believe. One of Kepler's law, which is that the orbital period squared is proportional to the radius cubed. So using that, we can immediately solve for Mars' orbital period, because we know that the radius of his orbit is 1 point times that of Earth's orbit. So that means that since we're gonna have imagine we're using Earth's period and radius as a base a benchmark, right? So we know its period is 1 year. So we want to find how a change in the radius is going to change the time, which is we know for the Earth is a year. So the period for the Earth is 1 year. And we know that any change in the r cubed is going to equal the change in the period squared. So since we're changing the radius 1.5 times, we know that 1.5r, we're going to cube that and end up 1.5 cubed comes out to be 3.375. So now we know that this time is going to be 3.375 is the same change in the period. So times t squared. And this is going to be proportional to 1.4 or 1.5 r cubed. So now what we can do is just square root this to find the change in the period, which ends up becoming 1.84 times t. And since we know that t of the Earth is just 1 year, it's just going to be 1.84 years. And that's our final answer. Alright, question 6. The diameter of Mars is about 1/2 the diameter of Earth, and its mass is about 1/10 the mass of Earth. Find the gravitational acceleration on the surface of Mars. Okay, so this is a similar question to question 4, where we found the gravitational acceleration of that random planet. So this one, we're going to be using a similar thing. We know Fg is going to be equal to m1g, which is going to be equal to g m1 times m2 over r squared, and in this case I will change, over r squared. This will just be, I'll just say mass of the Earth, because we'll do of the Earth. So these m1s will cancel, and so we have g of the Earth is equal to gme over r squared. So we have the diameter of Mars is about 1/2 the diameter of Earth, which would also mean that its radius is 1/2 the radius of Earth's. So now we're going to have this equals 9.8, and we're going to use this as a benchmark. So now the gravitational acceleration on Mars is going to be g times the mass of Mars which we know is given to us as me over 10, and then times or over the radius squared, and the radius of Mars is going to be half the radius of Earth, so it's going to be r over 2 squared. So this is going to come out to be, once we simplify this square, it's going to come out to 2/5 g of Earth. And once we solve for that, we end up with 3.92 after we plug in 9.8 meters per second squared. That's our answer. All right. Question 7. So the mass of planet W is 1/100th that of Earth, and its radius is 1/4 that of Earth. If the weight of an object is 600 newtons on Earth, what would it weigh on planet W? So force due to gravity, this is a simple one, is going to equal 600 newtons on Earth, which equals g times the mass of the object times the mass of Earth over r squared. So we know that this is on Earth. Fourth gravity on the planet that we don't know, planet W, is going to be g m1 times me over 100, that's given to us, times r over 4 squared. And once we simplify this, we will end up getting, I believe, 4/25 times the force due to gravity on Earth. So when we do 4/25 times 600, we end up with 96 newtons. That's our final answer. All right. Move on to question 8. An object weighs 90 newtons on Earth's surface. Determine its weight when it's 2 Earth radii from the planet's surface. So, force due to gravity, once again, g m1 times m2, which is the Earth, over r squared. But now, our new force due to gravity, let's do it as 2, is going to equal g m1, still m2, but this time, this is important to read carefully. Its weight when it is 2 Earth radii from the Earth's surface. So this is from the center of the Earth to the surface. It's 1r. But now we're doing 2 more. So it's not just going to be 2r on the bottom. It's actually 3r. Because it's adding 2 to the 1 initial. So now when we do this, we'll end up just getting it's 1/9 times this equation times the force due to gravity, which was given as 90. So 1/9 of 90 is just 10 newtons. That's our final answer. All right. Number 9. Consider a satellite orbiting a planet. The period of the satellite does not depend on the... So, for this one, it's just a pick which ones are correct. So, we talked about before how t squared is going to be proportional to r cubed. So, right off the bat, we know that the orbital radius does affect it, because we know just from this fact that any change in the radius will affect the period. So we can rule out 2 right away. Orbital radius the period does depend on the orbital radius. So now we have to determine if the mass of the satellite matters or if the mass of the planet matters. So in order to derive this equation, or I guess not to derive this equation, but to find period, what do we have to do? Well, we use this equation once again, as we always do, is g m1 times m2 over r squared, right? Which is going to equal, now we're going to set this equal to the force centripetal, which is going to be the mass of the object times v squared over r. Because when this object's in orbit, it's going to be, we're going to have like a planet like this and an object like this. It's going to be moving around in orbit, right? But at any given point, it's got a linear velocity in one direction, and the force is what keeps it orbiting. So the centripetal force is given as mv squared over r. So using this, we can start to cancel because the velocity is what's going to be able to give us our period. And I'll show you how that works in a second. But we can cancel out the m1s and cancel out 1r. So we have g times the mass of the planet over r equals v squared. And when we solve for v, we have v equals root g times mass of Osea's Earth over r. And now this is how fast it is moving. So we know the distance, the total distance, we know that velocity is equal to meters per second, which is just distance over time, right? And the period is in time. So if we're trying to solve for s, we get s equals m over velocity. And we have this term for velocity. So what's the term for meters? Well, it's just going to be the circumference of this orbit, which is 2 pi r. So that means that our period is going to equal 2 pi r over our velocity, which is g me over r square rooted. And we can see that m of the planet is in there, which means that it does have an effect on it, but the mass of the satellite isn't, so it does not depend on it. So our answer is only 1, the mass of the satellite. That's our final answer. All right. And then question 10. A satellite with mass of 9.0 times 10 to the third kilograms orbits 2.56 times 10 to the seventh meters above Earth's surface. Determine its period. All right. So, I just showed kind of how to find the period. So actually, I'm going to take that work back. And we have this right here. The period equals 2 pi r over root g times mass of the planet over r. And so I'm going to simplify this actually as 2 pi r times root r over root gm of the planet, which r times root r is just going to be r to the 3 halves. But I'll leave that there right now. So now all we have to do is plug in numbers. We have the satellite's mass, which we actually don't need, but we have how far. We have its radius, so 2 pi times the radius times the root of the radius over root of g, which is the constant, times the mass of the Earth, which is also given. The mass of the Earth, which is also given, and we end up getting our answer as 57,000 seconds approximately. And that is our answer. All it takes is deriving this kind of equation and then plugging in numbers. All right. So then number 11, determine the maximum height and Earth radii attempted by a vertically launched missile with a speed that is half the escape speed. So the escape speed is defined as just enough speed to escape the atmosphere, like just enough speed for the object to escape the atmosphere, so no excess speed. So also on the formula sheet, along with force, is the potential energy due to gravity, and that is given as negative g times m1 times m2 over r. So in order to find escape velocity, we can use conservation of energy. So this is our potential energy, and then kinetic energy, as always, is just 1/2 mv squared. It's going to be m1. So at the beginning of the object's motion, we're going to give it some velocity, and we're going to have this be the escape velocity. So this equation, we're going to have, I'll have conservation of momentum. So I'm just going to delete this right now. These are our initial values. And then plus 1/2 mv squared is going to equal final values. And its final values, we're going to set the velocity will be 0 because it'll just make it. So that will cancel. But then also the potential energy we're going to set as 0 at that point as well. Just at the end of the orbit. Which is why this number is negative. Because we're setting it to 0 at that point, at the edge of the atmosphere. So that means this whole side is canceled out to 0. And we can use this and we can solve for VE here, and this will give us our escape velocity. So what this is telling us, we know this is true. And for number 11, the maximum height it attains with a speed that is half the escape speed. So now what we want to do is change it from VE to VE over 2 and see how this changes our values. I will start by first solving this equation for VE. So it's V initial. Our VE is going to equal, I'll first have brought this over, so it'll be, actually we can cancel these M1s out right away, first of all. But we have VE is going to equal G times M2 over R, and we'll have a times 2 to cancel out the 1/2, and then all square rooted to cancel out the square root. So our VE, which is technically the initial velocity, our escape velocity is going to be root 2 times G M2 over R. But it is given that we're going to have an initial velocity of this times 1/2. So now all we have to do is figure out how high the object will go given this value. And once again, we can use conservation of energy. So we'll have its initial potential energy is going to be negative G M1 times M2 over R, and its kinetic energy is going to be plus 1/2 M1 times V squared, which is going to be 2G M2 over R, or 4R, because the 1/2 will also be squared. So this will cancel, and this will end up with just a 2 on the bottom. But then times this 1/2, so it'll end up being M1 G M2 over 4R. So I will rewrite that for simplicity. M1 G M2 over 4R. And this is going to equal it's going to equal, we're going to do potential energy once again, negative G M1 M2, and this time over, we're going to have the starting value R plus the H it gains. And we're going to be solving for H. So this R isn't actually squared, it's just R. So now we can solve this equation. We can actually cancel out all these M1s and the G's and the M2s. And we end up, I'll rewrite it up here, negative 1 over R plus 1 over 4R equals negative 1 over R plus H. And once you solve for H, you end up getting H is equal to R over 3. And that is how high the missile is able to go. All right, and then finally, number 12, a 0.6 kilogram object with 20 newtons on the surface of an unknown planet. The radius of the planet is meant to be 4 times 10 to the 6th. Determine the gravitational acceleration at a distance of 2 times 10 to the 6th directly above the surface of the planet. Okay, so we'll start off writing this equation. It's gm1 m2 over r squared. And that's going to equal 20 newtons. Right, so what I want to find is now when the change equals 20. But now we have gm1 m2 over, it's going to be r plus that extra distance, so 2 times 10 to the 6 meters. What does this equal now? And once we find this, we'll be able to find the gravitational acceleration. So what we'll actually notice is the initial radius is 4 times 10 to the 6 meters, and the extra distance is 2 times 10 to the 6 meters, which is exactly 1/2 of this initial value. So this value here is just going to be the same as 1.5 times r. This is also squared, which means we will end up getting the new FG at this new height is going to be over 1.5 r squared, which turns out to be gm1 m2 over r squared times 1 over 2.25 when you square the 1.5. And so when you divide 20 by 2.25, you end up getting, sorry, 1 second, 8.88 repeating. And now we know this is going to equal m1g, and we want to solve for g. We have m1 equals 0.6. So when we do 8.8 divided by 0.6, we'll end up getting g equals 14.8 meters per second squared. And that is our final answer. So that is problem set 13 for AP Physics C. I hope it was helpful in your understanding of gravity and how to use the equations. So thank you for watching.